learning outcomes for this class are being able to understand the concept of instantaneous center of zero velocity, and then to use that concept in order to solve for the angular velocities and linear velocities of points on a rigid body. Okay. So I'll first introduce the concept with a simple example. Concept of instantaneous center of zero velocity. Okay, so in the previous class we have seen VB is equal to VA plus omega cross RP with respect to A as the equation which describes the motion of point B with respect to A. Now, if the velocity of A is 0, then we see that VB is omega cross RB with respect to A, or in other words, if you look at the magnitude of VB, it is simply the magnitude of omega times the magnitude of RB with respect to A. So this point A, which has a velocity of 0, is called the instantaneous center of zero velocity. Okay, in short, it's called IC, and that's the notation I'll be using throughout this course. So to give you an intuitive understanding of this, if there is a link, this is point A, this is point B. If this is the instantaneous center, the velocity is 0. B is going to have a velocity which is going to be at right angles to the vector drawn from A to B. So this is a vector R B to A to B. VB is going to be this way only if the angular speed of this body is in the anti-clockwise direction or counterclockwise direction. Okay, so this point here, A, is called instantaneous center, IC, of zero velocity. So there are some important things about the IC. So first thing is that the IC may be located outside the body. The second fact is that IC may change with time, and the third fact is that IC may be at infinity. Okay, so a couple of examples which will further illustrate IC. Examples: rolling wheel. Okay, a rolling wheel has the property that one point which contacts the ground has a velocity of exactly 0, right? So if you draw lines like this, you can find the velocity of different points on the body. Next one is a pinned or a hinged link. So a pinned link has the property that the point which is pinned has a velocity equal to 0. So if you want to find velocity of any point, it's just going to be in a direction normal to the vector from IC to that point. Finally, a translating link. Okay, it moves if any 2 points on the links are moving with the same speed in one direction, we'll have its IC at infinity. Okay, so let me now tell you how to locate the IC for different cases. So locating the IC. Okay, first case. So this is the body, and let's say that you know the velocity of a point and you know the direction of the velocity. You also know the angular speed. So v p omega is given. You're told to find r p I c, which is the length of the instantaneous center of zero velocity with respect to p. All you got to do is, in this case, is draw a line perpendicular to vp, okay, and the IC would be on this line, right? You don't know the location. You know it's going to be on this line, but you don't know the exact position. To get the exact position, we use the formula Vp is omega times r p with respect to IC, and so Rp with respect to IC is Vp divided by omega. So this is going to be a vector pointing this way, Rp with respect to IC. So knowing Vp and knowing omega, you can find Rp with respect to C. So this is only when you know Vp and omega. Sometimes what might happen is, for the rigid body, you may know the velocities of 2 points only. Okay, you know the velocity and direction, and you're told to find the IC. In this case, what you'll do is you'll draw a perpendicular to A and perpendicular to B, right? And wherever they intersect is where the IC is going to be located. So this is going to be RA with respect to IC. This is going to be RB with respect to IC. And if the angular speed of this body is omega, which is an unknown, then we can see that VA is omega RA with respect to IC. It's omega RA with respect to IC, and VB is omega RB with respect to IC, right? So we can, in this case, find the ratio of the two, simply VA divided by VB, which is also happens to be omega. So given VA and VB, we can find the ratio of RA with respect to C, RB with respect to C, but we cannot find the individual values unless we're given some more information. So for example, if we're given the distance between the two, we might be able to find the IC, the exact location of exact value for A with respect to C and B with respect to C. The third case is a similar case where you are given the velocities, but they are pointing in opposite directions. So VA, VB. In this case, you use the same recipe. Says you draw a perpendicular to A, or perpendicular to B, and the IC is going to be located where lines perpendicular to A and B will intersect. So IC. Okay, so in this case, the same formula which was used, this one applies. You could also get a case where VA and VB are parallel, like so. Use the same recipe, which is basically draw normal to A and B, and the IC should be located somewhere on that line. Okay, again, the formula for IC in this case is going to be the same as the one we derived earlier, the same formula. This formula is going to be used. It's 2, 3, and 4 cases. This is 4, have the same formula for the IC. Okay. Okay, so the key is, if you know the velocity of the point of interest, then you need to draw perpendicular to that velocity vector in order to get the IC. If you have 2 points, then you can find the point of intersection of the normals to get the location of the IC. Okay, let's try to use what we learned so far in order to solve some problems. So here's a basic question. You're given 3 different geometries. You got to find the IC for link AB for each of these cases. So let's start with A. Okay, now in order to draw the IC, the simplest thing you can do is, first you want to find, so we want the IC for AB. Okay, now my question to you is, do you know the velocity of any points on AB? Well, you do know the velocity of point A. The velocity of point A is going to be, since this point is moving with 0 velocity, and this link OA moves clockwise, the velocity of A is going to be in the direction shown, right? Similarly, the slider is going to move along the ramp. Okay. Now, once you have drawn the velocity vectors of 2 points, in order to get the IC, all you have to draw is the normals to those velocity vectors. So in this case, the normal to A is just this, the normal to B is this, and the point where they intersect is the IC. So this is the IC for link AB for part A. To redraw this, okay, C, B, A, and we're given that OA, let's call this OA moves clockwise. Okay, so same recipe, what we do is first find velocities of points of interest. So we know that the velocity of A is going to be this way, because OA moves clockwise. The point C, or in this case, well, C moves along this. So we know that. So once we have found the velocities of 2 points, all we do is draw the normal to the velocities, and it looks like this is going to intersect way here. I see. Okay, moving on to the third question. C. Okay, again, we need to find the IC. So what we do is find the velocities of 2 points. Uh, since this thing is going to turn, since the disk is going to turn in the counterclockwise direction, and since this is assuming that it is going to simply roll, uh, so it's assuming that it's going to roll, this point is going to have zero velocity. So the point here, this point is going to, so I'll call no slip. So that's at 0, which means that any point, if you draw a line like this, then the velocity of point A is going to be along the direction shown. Okay. Now note here that the IC for the disk is here, but that is not the same as the IC for AB. AB will have a different IC, as we'll see. So this thing is right angle. Okay. Since this thing is moved, the disk is moving counterclockwise, B has a tendency to move to the left. So I'm going to draw the vector like this. Now all I need to do is draw normals to the velocity vector. So this is the velocity vector, the normal to the velocity vector is like this. This is the velocity vector for B, the normal to the velocity vector looks like this, and the intersection is right here. So that is the IC. Okay, so one thing to note is the IC for AB is right here, while the IC for just the disk and the ground is right here. Okay, they are not the same. Each link will have a different IC. Not only that, the IC will change with time, so this point would move with time. Also note that the IC in this case is not on the board. In fact, for all the problems we've seen here, A, B, C, the IC is not on the links. It's outside the body, and that's perfectly fine with the Instantaneous Center. It doesn't have to be on the body. Okay, let's solve another question. It's slipping. So due to slipping, points A and B on the rim have velocities of 10 and 5 feet per second as shown. You got to find the velocity of the center point C and point E. Okay, now this question, you can do this question using what you learned in the previous class. It's absolutely fine. Just that using the Instantaneous Center might make this problem simpler to analyze. So let's solve this using the concept of Instantaneous Center. But as I said, this is not the only way. You can use what you learned in the last class. So the first thing I want to do is I want to be able to draw the Instantaneous Center. Okay. The reason I'm doing it is that because I want to first find the angular velocity of the disk. If I find the angular velocity, then I will be able to solve for velocity of E and velocity of C, right? Because velocity of E would depend on, and C would depend on the angular velocity. So my goal is to find the angular velocity of the disk, which is not given to me. So let me draw first the disk, draw the velocity vector. Next, I want to find the IC. So for that, what I do is I draw a normal to the velocity vector. This is the normal. Another normal for the other velocity vector, and wherever they intersect. So they'll actually intersect on the line which passes the center, but the center is not the IC, as you'll see. Okay, so I don't know what the IC is. Let me just say that the IC is right here. We'll find the exact value in a bit, but let's say that the IC is there. Let's call the distance from point A to IC as D. So let's call it X. Yeah, let's call it X. And so X is the distance of the IC from A. We know that this distance is twice the radius of the circle or the disk is about 1.6. So which means that this distance is 1.6 minus x. Okay, knowing that, let us try to apply the IC formula. It says that the velocity of point A is going to be the velocity, angular velocity of the disk times the vector A to IC. Similarly for B, there's an omega times R B with respect to IC. Okay, so let us try to find the velocities of the 2 points. So in terms of angular speed, so velocity of A is 5, angular speed is unknown. The distance from A to IC is x. Similarly, velocity of B is 10, the angular speed is unknown, and the distance from IC to B is, as we've written there, 1.6 minus x. So we have two equations and two unknown, so we should be able to solve it. So let's take the ratio of 1 to 2. So that's going to be 5 divided by 10 is equal to x divided by 1.6 minus x. And so if you try to solve this for x, you see that x is 1.60, sorry, it is 1.607 feet. Okay, once you know x, you can find what omega is. It's simply 5 divided by x from 1, so from 1, so then omega is simply 9.37 radians per second. Okay, now we have found the angular speed. Now we are in a position to find the the velocities of point E and C. Now again, you can use what we learned in chapter 60, section 16.6 previous 16.5 previous class, but we'll just use the IC to find the velocities of E and C. So E is right here, okay, and C is right here, and I know that the IC is 1.067. Okay, I'm going to redraw the figure because it looks like the IC is somewhere on top, because this distance is 0.8, right? So it has to be on top. So redrawing the figure, the IC is here, this is C, this is E, this is 0.8, so this distance has to be 1.067 minus 0.8, and that comes out to be 0.267. Okay, so I have that. All I need to do now is use that to find the velocity of point E. So E is on the circumference of the circle in line with the center C. So IC is the point where the velocity is 0, right? So what I do is I draw a line from IC all the way to E. So that's going to be RE to IC. And then all I need to do to find the velocity is draw a normal to this line. So the normal is this way. So this is going to be velocity of E. Similarly, I will draw a line like this. This is the vector RC with respect to IC. And so the line normal to this gives me the velocity. So this is going to be VC. Okay, so having drawn that, I'm now ready to apply the instantaneous center formula. VC is omega times RC with respect to IC. Omega is 9.37. The distance from IC to C is simply 0.267. So the velocity of point C is going to be this comes out to be 2.5 feet per second. Okay, if you want to find the velocity of E, it's omega RE with respect to IC. Omega is 9.37, and the IC can be found from the fact that it's the hypotenuse. It's going to be the square of this distance, which is 0.8, or the radius square, plus 0.267 square. Looks like the previous answer just disappeared. I'm going to write this as 2.5. Yeah, it's 2.5. So if you do this math, it comes out to be 7.9 feet per second. So that's the answer. Okay, so we found the velocity of point E and C using the IC. So let me just summarize what we did. We have a disk which was slipping, and you were asked to find the velocity of 2 points on the disk. So what we did was we tried to first find the angular speed by using the concept of instantaneous center. So once we got the angular speed and the instantaneous center, we were able to find the velocities of point E and C by using the angular speed and the position of the instantaneous center with respect to those points. Okay, this dramatically simplified the logic and the calculations. Otherwise, you would have to use the formulas which you learned in section 16.5, which are also fine, but I think it would be more computationally heavy. Okay, so the final problem I want to do is this problem. Okay, let's read the question. The question is, you got to find the angular velocity of link AB at this instant that the block C is moving upwards with a velocity of 12 inch per second. Okay, I have redrawn the figure to help me with solving this. Okay, so I want to know the angular speed of AB. Okay, again, you can do this problem using 16.5. All you will have to do is find the velocity of B, find the velocity of C, and then try to link them up, and you'll be able to solve for omega AB. But we will solve this problem using instantaneous center. Okay, the idea is that if we can find the instantaneous center for link link BC, then we might be able to solve for omega AB. So let us try to find the instantaneous center for link BC. Okay, C moves upwards, right? B moves since omega AB is counterclockwise, the angular speed of B is the linear velocity of B is going to be in this direction. It's going to be 90 degrees with A, so this angle here is going to be 45 degrees. Okay, now note that the instantaneous center for AB is at A because this is at 0 speed. However, we have to still find the instantaneous center for link BC. So what I do is I draw a normal to velocity of C. I draw a normal to this velocity vector, velocity B. It has to be on this line. And this intersection gives me the IC. Okay, so that is the IC. Okay, and I think that will help me to find omega AB. Okay, so given that, I think one way to do this is to find the position of it would be if we can find the length of the IC from C to IC and IC to B, then we might be able to relate the velocity of C with B and use that to find angular velocity of AB. So let's just try to do that. So first thing is to find the location of the IC. Okay, uh, we know that it is on link AB. Okay, so let's just use the geometry to figure out the IC. This particular triangle ICCB, let's try to get the angles for that particular triangle. Okay, so we know that this is 45, this is 45, this is 30, so this has to be 30 degrees. So we've got this side. Okay, what else can we get from this triangle? Can we say something about this angle? Well, if this is 45, then this should be 45, which means that this angle should also be 45. Okay, so if this is 45, this is 30, and this is 90, then this angle here is going to be 180 minus the sum of all the remaining angles. So it's going to be 45 plus 90, which is 135, plus 30 is going to be 165, which means that this angle here is going to be 15 degrees. Okay, so in other words, this is how the triangle will look. 45, 30, 100 and so for 90, 105 degrees. So the sum is 180 degrees. Okay, so this is IC, this is C, this is B, and we also know that 4 is the length of link BC. Okay, so now there's one property about triangles, is that if you know one side and 3 angles, then you should be able to find all the sides of the triangle using what is known as the sine rule. So the sine rule says that 4 divided by the angle which is opposite to the side, so 4 divided by sine 45 should be equal to length RB with respect to IC divided by the angle opposite this side, so it's going to be sine 30 degrees, should be equal to RC with respect to IC, which is this side, divided by sine of 105 degrees. So here we have two unknowns and two equations. This is one equation, and you can think of this as another equation. So we can solve for RB with respect to IC and RC with respect to IC. So RB with respect to IC is 2.82 inch, and C with respect to IC is going to be 5.46 inch. Okay, so we've got the lengths of the IC. Now let us move on and try to find the angular speed of AB between velocity of C and velocity of B. Velocity of B is omega times RB with respect to IB. VC is going to be omega times RC with respect to IC. So we know what the we know what VC is. We don't know what VB is. We don't know what omega is, but we know what RB and RC is. So in this case, I'm interested in finding VB, and it will be clear why I'm interested in VB. So I'm going to take the ratio of the two. VB divided by VC is RB with respect to IC divided by RC with respect to IC. So RB with respect to IC is 2.82. RC with respect to IC is 5.46, right? VB is going to be 2.82 divided by 5.46 times VC. Okay, so VB is that, but we also know from the fact that point A is the instantaneous center, we know that VB is also omega AB times RB with respect to A, which is omega AB times the length of AB, which is 5. So from 1 and 2, we can write 2.82 divided by 5.46 VC is equal to omega AB times 5, but VC is given to us as 12. So this is one equation, one unknown in omega AB. Omega AB comes out to be 1.24 radians per second. So that's the answer. Okay.